Welcome back, General Chemistry. I'm so excited. Let's tackle limiting reactants. This is our last video in our series of moles. So this is still part of, this is Unit 3, not Unit 4. This is still part of Unit 3. We are tackling all of our mole sections, and then we're going to turn around and classify reactions. So that'll be our next series of videos. This is our last set for moles though. So grab your periodic table and your calculator, and let's see if we can't work our way through some problems. Now I love these. They're the most complicated out of all of our moles problems, but they're still doable. So I went ahead and threw all my tricks in there. Notice I am just all words and names, and instead of giving you just one starting material, I've given you two starting materials. So this is how we can look at it and identify right away. We're going to have to figure out which one is limiting. So let's start with our process. We've already gone through our couple of videos. We know right now that we've got trust issues. So the first thing we're going to do is write the actual reaction. And then of course, you need to grab your yoga pants and light a candle because we are going to find our balance. Then we can do some math. So let's start. It sounds like we've got ammonia and copper oxide reacting. So let's put those over in our reactants. And then copper 2 oxide, why does that matter? Oop. That is going to tell us how to put together that formula. That is a nice ionic compound. And then it says that it forms copper. All right, so just elemental copper, it looks like. Water, we know what that is. And nitrogen. Don't forget that nitrogen is one of your diatomics. That is N2, not just N. Okay, remember your list of diatomics. Let's run through them real quick again. Your diatomics are hydrogen. If you're looking at your periodic table, they kind of make a 7. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, all of those in their elemental form are a 2, and I'm just going to put the name in on your homework and on your test. So you've got to know that 2 is there, especially when we need to find our balance. That's going to matter. All right, so let's take this, and now we need to balance it. Let's spell out what we've got on each side. We've got 1 nitrogen over here, 2 nitrogens over there. Right away, we're not balanced. Something's got to give there. All right, we've got 3 hydrogens. Over here, we've got 2 hydrogens. We've got a copper and an oxygen. Over here, we've got 1 copper and 1 oxygen. Okay, well, maybe that's not going to be too bad. All right, first things first, we've got to fix this nitrogen. So let's add a 2 over here. And so that's going to bring us to 2 nitrogens, but that just jacked with your hydrogens. So now we've got 6 hydrogens. So what do we need to do over here? We need to go up to 6. So I'm going to add a 3 there. All right, well, holy crap, that just messed with your oxygens. So how many oxygens do we have now? 3. Oh my. Okay, how do we get to 3 oxygens over here? We've got to put a 3 there. Well, son of a motherless goat, that just messed with copper. All right, so now you've got 3 coppers here. We need to go to 3 coppers here. Whew, that was kind of fun. All right, so before we do any math, we have to have that whole reaction balanced. We just balanced everything. Let's go ahead and erase that. Now we can look at the math. Okay, we just spent the last video learning how to do that mole ratio and taking an amount of reactant or product and literally doing the unit conversion to convert it into anything else the question might ask. We're going to do the exact same process, but here's one major difference. In this question, we're given 10 grams of ammonia and 10 grams of our copper oxide. Okay, now if you just look at that on inspection, you're thinking, done. I've got the same amount of both of them. That's a deal. I'm done. Well, it isn't, because remember, number one, both of these substances weigh different. Ammonia and copper oxide are going to have different molecular weights. And number two, you just balanced your reaction and you don't need 1 and 1. You need 2 and 3. So we've got a whole mess going on here. And what we need to figure out is, out of this 10 grams of ammonia or 10 grams of copper oxide, which one are you going to run out of first? That is our limiting reactant. You're literally the one that you are going to run out of first is going to limit your whole reaction. It's kind of like baking cookies. If you're making chocolate chip cookies and you need a whole bag of chocolate chips and you only have a fourth of a bag, are you totally screwed? No, you make a smaller batch. You scale everything to your chocolate chips. So, all right, let's figure out then, all right, which one is actually going to limit our reaction? So what we could do, let's go ahead and calculate both of them and convert them into nitrogen and just see which one wins. I mean, that's the easiest way to tackle these problems. We'll do a little bit of math here. Let's start our process. We've got 10 grams of ammonia, and we're going to convert, just like our last video, let's convert it to nitrogen. So let's take and calculate our moles. Let's use our mole ratio. Let's convert that to nitrogen. And then let's go right back to grams and let's see how much we can make. All right, we always kind of set up our units first, make sure we're on the right track. We can cross off our grams of ammonia, cross off your moles of ammonia, moles of nitrogen, and end up with grams of nitrogen. All right, let's fill in some numbers there then. If we've got our ammonia, let's figure out our molecular weight. I'm going to go ahead for this one because I'm going to run out of space. I'm going to go ahead and just do whole numbers if that's cool. Nitrogen is 14 plus 3 hydrogens, so I'm going to go 17 on this one. And then our mole ratio, we have for every, let's see, 2 moles of ammonia, we're going to make 1 mole of nitrogen. And then I'm going to go whole numbers on this again. For our N2, what is that weigh? 2 times 14, 28. All right, let's throw that in our calculator, see what you get. 10 divided by 17 divided by 2 times 28. All right, well, you get a syntax error. That's what you get. Let's try that again. That's awesome. All right, I am getting 8.24, and I rounded for 3 sig figs on that. That is how much we could possibly make from that 10 grams of ammonia. I love it. So, I mean, the easiest way to tackle this problem is turn right around and do this again with the 10 grams of copper oxide, and let's see how much nitrogen we could make, and let's compare them. Let's do that whole process again. We've got grams of copper oxide, moles of copper oxide. We've got our mole ratio. We're going to convert to nitrogen again. Let's double check we've got that lined up all right. Yeah, we've got moles we could cross off. All right, let's add some numbers. Grab your periodic table. What's copper worth? Let's see. I've got 63.5. And I'm going to do 16 for oxygen. So this is 79.5. And then what's our mole ratio? For every 1 mole of nitrogen, we need 3 moles of copper oxide. And then our grams of nitrogen again is 28. All right, let's put that in on our calculator. Right, divided by 3 times 28. I am getting only, okay, slow down here. I'm getting only 1.17 grams of nitrogen. Holy cow, that is so different. Check that out. If you start with 10 grams of ammonia, you can make 8 grams of nitrogen. But on the other hand, if you have only 10 grams of your copper oxide, you're only making 1 gram of your nitrogen. So look at that. All right, between these two reagents then, which one is going to be your limiting? Well, that's going to be your copper oxide. And why? Because you are going to run out of that copper oxide before you run out of your ammonia. You can only ever make as much as your smallest reagent will let you make. That by smallest reagent, I mean that limiting reactant. So if your copper oxide is only going to let you make 1.17 grams, that's all you can make. What would matter then, what that means is then you're going to have an excess of nitrogen, and you just aren't going to react. I'm sorry, not an excess of nitrogen, an excess of ammonia, and you're just not going to react at all. You're just going to leave some behind. That's all. All right, so that's our concept of a limiting reactant. How can you spot those problems? Well, you can spot them when you're given the amounts of all of your starting materials, and you literally have to compare those amounts. So this is the most straightforward way to do it. It seems like it's a lot of work, but we've already done these problems before. You're just going to do 2 instead of 1 and compare your amounts at the end. Okay, I love it. Let's try another one. All right, we're going to do this one again. Notice I went super sassy and I just gave you the words again. All right, so if the reaction of hydrogen and carbon monoxide produces methanol. All right, done. How do we know how to write that? All right, if the reaction of hydrogen is one of our diatomics, and carbon monoxide, all right, that's carbon and monoxide, and we are making methanol. Okay, I love it. And we're starting from 5 grams each. Well, that screams limiting reactant right there. You're given both starting material amounts, so we know that that's that kind of problem. Except, are we ready to start? Oh, Sal, no. We have got to find our balance first. So let's take a second and let's figure out, we've got 2 hydrogens, 1 carbon, 1 oxygen. So over here, we've got 4 hydrogens, 1 carbon, and 1 oxygen. So we've got to do something to our hydrogens then, huh? We just need to go to 4 hydrogens over here. Well, that's not too bad, is it? Okay, I love it. All right, we've got a nice balanced reaction. And we've got 2 amounts. Let's turn right around and do some math. Let's do the same thing. Let's compare both of them. Start with 5 grams of hydrogen. Convert it to moles. Use your mole ratio. And then let's convert it to grams. And let's see how much we could possibly make. All right, just like the last, I'm going to go ahead and just use whole numbers again. So if I've got 1 mole of hydrogen, that's H2, that's 2 grams. All right, look at your mole ratio then. For our hydrogen, we've got a 1 to 2 mole ratio there. And then what about our grams for methanol? All right, well, 12 for carbon, plus 4 for hydrogen, plus 16 for oxygen. I am getting 32 grams per mole for our methanol. All All right, grab your calculator. Let's try it. I've got 5 divided by 2 times 32. I get, good Lord, I get 40 grams of methanol from 5 grams of hydrogen. That's a lot, huh? All right, let's put a little sparkle pen around there. Remember from our percent yield, what we're calculating is how much we could possibly make. This is our theoretical. This is in a perfect world, all the stars align. If we have an excess carbon monoxide, 5 grams of hydrogen, that's how much we can make. Let's turn around and calculate the same thing now for 5 grams of carbon monoxide. And let's convert that to methanol and see how much we could possibly make. All right, so let's convert to moles. Let's use our mole ratio. If you're getting to the point where you feel like, oh man, this is getting repetitive, all these videos and all we keep doing is this mole ratio, awesome. Then you get it. Then that's good. That's not a bad thing. Okay, and then let's convert that methanol to grams again. And let's see how much we could possibly make. All right, a carbon and an oxygen, that's what, 12 plus 16. All right, so 28 grams here. What's our mole ratio? We've got 1 mole of methanol, 1 mole of carbon monoxide. And then let's put our 32 in again here. All right, let's do some math. 5 divided by 28 times 32. I am getting only 5.7 grams of methanol. All right, holy cow. All right, which one is your limiting? Obviously, your smaller amount is your carbon monoxide. So if you mix 5 grams of hydrogen and 5 grams of carbon monoxide, you are going to use up that carbon monoxide first. You are going to run out of carbon monoxide before you run out of hydrogen. So what would happen in your reaction then is you're going to make 5.7 grams of methanol and you are going to have a whole lot of extra hydrogen. Okay. Awesome. So I hope that kind of makes sense. Let's do one more. Let's do one more of these and then we'll give you some homework to practice on these and trying some of this in on your Blackboard quizzes. All right, let's light some booze on fire. I mean, if you can't have fun doing that, wait, never mind. Don't do that at home. Could be dangerous. All right, so let's take ethanol and let's light it on fire. So that's C2. Okay, don't actually take ethanol and light it on fire. Oxygen, remember oxygen is O2. And then it's a combustion reaction. Now we learned our combustion reactions always make CO2 and water. So if we are going to figure out our carbon dioxide and we're given 1 gram of our ethanol, 1.5 grams of oxygen, okay, we've got to figure out our limiting reactant because we're given 2 amounts. But before we can do that, we've got to balance. So I think we balanced this one in an earlier video, but let's try it again. It's kind of fun. So we've got 2 carbons, 6 hydrogens, 3 oxygens. Over here we've got 1 carbon, 2 hydrogens, and 3 oxygens. All right, let's start with the carbon. Let's go 2 carbons here. All right, now that messed with our oxygen. So what did that just do to our oxygen? That gave us 5 oxygens. Okay, now on this side, we've got 6 hydrogens. Good heavens, we better go to 6 hydrogens here. How do we do that? We're gonna go 3 on our water. Okay, perfect. So what did that just do? That got us to balance everything except we just messed with our oxygens again. So now we've got 7 oxygens. How do we get 7 oxygens on the other side? We had a 3 there. And then we can get 7 oxygens. All right, beautiful, beautiful. Let's erase this part. Let's do our math. Okay, let's take both starting amounts and let's literally compare them and see how much carbon dioxide we could make. So let's take a gram of booze, convert it to moles. Let's use our mole ratio. Let's convert that to CO2. And then let's convert that to grams. All right, let's fill in some numbers. We've got, I'm going to go ahead and cheat again and use some whole numbers. So for our ethanol, let's see, we've got 2 times 12 plus 6 plus 16. I get 46. Our mole ratio, we've got 2 moles of carbon dioxide for every 1 mole of booze. Okay, and then what about our grams for carbon dioxide? 12 plus 16 plus 16. I've got 44. All right, let's go ahead and do the math for that. Hang on a second. Did anybody notice my brain freeze here? 46 should be down here. All right, so 1 divided by 46 times 2 times 44. I get 1.9 grams of CO2. Okay, let's compare that to our 1.5 grams of oxygen, and let's do the exact same process. Let's use our mole ratio again. And let's convert that to CO2. Let's see what we get. All right, for my oxygen, it's 32. And our mole ratio, what do we have here? 2 moles of carbon dioxide for 3 moles of oxygen. And then let's put in the 44. All right, let's compare. Let's compare. Grab your calculator. Divided by 32. I get 1.375 grams CO2. Aha! So we would run out of oxygen in this reaction. Literally, we could only make 1.375 grams of carbon dioxide. If this is indeed a combustion and it's on fire, you just smothered your fire. You just ran out of oxygen first before you ran out of the fuel part. So our limiting reactant is going to be, oh, that's just fluffy. Hang on. So our limiting is going to be the oxygen. Okay, so that means we would use up all of our oxygen and we would have leftovers in our ethanol. Okay, I love it. I hope you enjoyed this video. Try some of these. These are our last series of mole videos. We're going to have a couple more videos coming in our Unit 3, and that is classifying reactions.